good. Bonjour.
How are you?
I'm very well, thank you. And your good self?
Yeah, I'm okay. A bit tired.
Tired.
Yeah, a bit tired.
Why? Do I ask or better
I'm
not?
crying all night about the tragic
Sorry?
news. I'm crying all night about the tragic news. Do you hear about it?
Depends on. If you
Us.
talk about
Us,
Kobe,
yeah. Very emotional. Very unfortunate.
good man.
I've never really been emotional about celebrities passing away. It doesn't really affect me. I always think in my head it's kind of like, you know, no one's going to be posting on news outlets when I pass away. So, you know, it's unfortunate, but nothing to cry about. But this is actually quite unfortunate.
Hello. Hi.
First player I ever followed when I got into basketball.
Oh, really?
So it's fun.
Yeah.
Horrendous way to go as well.
Well, I'd rather die in a helicopter crash than slow and painful and, you know, sort of dementia or something like that. But, you know, I'd rather not die, full stop. But then, on the other hand, the problem is that life is fatal.
Happens, isn't it?
Yeah. So, it's what happens. No.
Please.
No, I'm starting in 1 minute.
1 minute, okay, I'll do 1 minute.
Okay. A most wonderful good after morning, ladies and gentlemen. Different venue, same old me. So here you see what we are going to do today in this session. We've got quite a big schedule this week. I think we've got 4 sessions for BI 301, which I personally believe should be against the Geneva Convention for the prevention of cruelty against students and lecturers, but hey ho, that's life. So what we are going to do in this session is I will show you how we can calculate the turnover number, or K-cut, for an enzyme. We will briefly discuss how you can calculate specific activity. And also one of my favorite exam questions, how you calculate the substrate concentration at a given rate. Please don't forget, it's attendance monitoring. Go to Moodle BI 301 and tell me that you are here. Not that I do care about that, whether you are here or not. The important thing is that you learn the stuff. Wherever you learn it, that's up to you, really. But, you know, the university wants that. Also, as you are aware, quiz 1 for BI 301 is open. It's in your email. I think, I don't know whether I've put it on the group chat, but I think all the information is there. It's also on Moodle. If I remember correctly, the deadline is, can't remember, on Sunday. It's on the 2nd. So that's the Sunday. Yeah. On the 2nd Sunday, no, on Sunday the 2nd at 5 p.m. These are easy marks, right? You can do the test as often as you like. Easy marks. I've seen some really shocking gameplay in the BI 308 quiz. How on earth anyone can offer me a 0 out of 19 as I mean, if you think about it, even if you are a monkey and do just random answers, you should have a 20% chance to hit it, right? How you get 0? Well, obviously you are not a monkey. Okay, so in the last session, we discussed the 3 critical enzyme parameters. Whenever we are dealing with enzymes, and basically enzymes are dealing with us a lot, we said there are basically 3 parameters that are absolutely crucial if we want to characterize an enzyme. So, for example, Vmax, That is really the maximum speed at which an enzyme can perform the reaction. It is a theoretical number because you will never reach Vmax in reality. It means when every single enzyme is dealing with a substrate molecule at any given time. And therefore you see it's only a theoretical number. But Vmax, we get Vmax from the interpolation of some experimental data. Vmax tells us basically how the enzyme behaves when the substrate concentration is, well, in theory, infinite, but it tells us really what happens if the substrate concentration is very, very high. We said Km. This is just simply an conglomerate of rate constants, and Km tells us something about the affinity of the enzyme for its substrate. So the affinity of the enzyme for the substrate. If Km is high, then the affinity is low, and the other way around. The affinity is low. I need a lot of substrate in order to get to a half maximum velocity point. And we said Vmax over Km. This tells us basically how the enzyme behaves when the substrate concentration is very, very low. And I showed you that we can determine very easily these three parameters when we do some experiments. And I showed you two different plots. My favorite one is the Eddy-Hofstee plot. In an Eddy-Hofstee plot, we just simply plot the rate over the substrate concentration on the x-axis versus the rate on the y-axis. And what we get is more or less a straight line. And if we extrapolate this straight line, we find that the intercept here, that gives us Vmax. The intercept with the x-axis gives us Vmax over Km. And the gradient gives us minus Km. You will come across other plots. My advice would be always go for Eddy-Hofstee. Do not ever, under any circumstances, just simply plot your data straight away in a Michaelis-Menten plot, because that's shite. And I would also strongly advise against this double reciprocal plot that you find in many, many textbooks. The reason for that is it's shite, right? Don't just, I mean, why on earth would you buy an old rusty bike when you can have a brand new Ferrari? Right? So always go for the Eddy-Hofstee. That is the plot. Now, what I want to do with you today is, in preparation for the project, for the mini project that you are going to do next week, and also the exam, I want to discuss with you how we can determine two more parameters. They're usually not considered as the essential parameters like Vmax Km and Vmax over Km, but they are quite important in real life when you are dealing with enzymes, with enzyme solutions. And let's go first for the turnover number, kcat. And I told you last week, kcat tells you how fast an enzyme actually can deal with a substrate molecule. And we said kcat basically equals Vmax divided by the total enzyme concentration. That is the equation that you will use if you are required to determine kcat. So here's a little scenario. So you measure the rate of an enzyme. You add 10 microliter of a 1 milligram per mil stock solution of the enzyme, and you have a total volume of 3 milliliters. And you will see that this is totally realistic, because that is what you're going to do next week. You then do your measurements, you do your plot, your Eddy-Hofstee plot, and you measure a Vmax of 1 millimolar per minute. And you also know that the enzyme has a molecular mass of, and here it comes, 100 kD. What on earth is a kD when it's at home? Well, protein chemists usually don't deviation gram per mole. Instead, they use very often, because gram per mole would give you a very, very large number if you are dealing with proteins. So instead, they use the abbreviation kilodalton. And kilo, of course, means 1,000, and Dalton is just sort of another word of saying 1 gram per mole. So what you have here, 100 kD, and that's commonly used when you're dealing with proteins. 100 kD actually just simply means 100,000 gram per mole, or 100 times 10 to the power of 3 gram per mole. So, what do we need in order to calculate our kcat? Our number, how often the enzyme actually can turn over a substrate molecule. Now, if we are looking at that, we have given a Vmax, so we don't need to worry about the Vmax. All we need to worry about is the concentration of the enzyme. So we really need to find the concentration of the enzyme. That is the one that we really need to do. So what are we doing here in this experiment? We have here our reaction vessel, whatever you want to call it. And we add 10 microliter of 1 milligram per milliliter stock. Okay? So now we have to figure out what is our final enzyme concentration that we have, and we want it not in gram per milliliter, we want it in molar. So, with that given, I would suggest you follow a certain order how you calculate that, because that's always, it's a little bit like cooking. If you've got a step-by-step guide, then there is a good chance that the cake doesn't get totally messed up, only a little bit, especially when I do it. But that is due to my inabilities, and not because I'm not following the right protocol. So the first thing that we should do in this case is, so the first step is, how many grams of enzyme are in the assay, in our 3 milliliter? Right, that's quite easy to do, especially when you use dimensional analysis. Or you can, bless you, but you can use, and again, you can use whatever method you fancy. It's entirely up to you. So we are looking for grams, and we have, here we have our concentration. We have 1 times 10 to the minus 3 gram in 1 times 10 to the minus 3 liters. Now we want the grams. The liters are a bit of a nuisance. Do we have anything else where we have liters? Well, yes, we have our 10 microliter, because that is the amount that we add into our assay. So we multiply that by 10 times 10 to the, what was micro in terms of scientific? Micro, 10 to the minus? 6, thank you. 10 to the minus 6 liters. Liters cancels out. That cancels out. Oh, hey, look, that was easy. We have 10 times 10 to the minus 6 grams. So we've got 10 microgram basically in our assay, in these 3 milliliters. Now let's convert, in the second step, let's convert the grams to moles. So we're actually looking for mole. So do we have mole anywhere? Yes, actually we've got mole here with our molecular mass of the enzyme. And we write it so that the mole is in the right position. So we have mole divided by 100,000 gram. Now the mole is in the right position. We just need to get rid of the gram. How do we get rid of the gram? Well, actually we multiply it by the amount of grams that we just calculated, that we have in our assay. That is times 10 to the minus 6 gram. And you see the grams cancel out. And all we need to do is find out what this gives us. And that is, if I didn't get it totally wrong, 10 times 10 to the minus 11 mole. Have I done it right? Some quality control? I think I have. So now let's calculate our concentration of the enzyme. We know that we have these 10 times 10 to the 11 mole in 3 milliliter. So we have concentration equals 10 times 10 to the minus 11 mole in 3 times 10 to the minus 3 liter. And if you put that into your calculator, you will get 3.33 times 10 to the minus 8 mole per liter. Have I done it right? Looks okay? Yeah? So that is our enzyme concentration that we're dealing with. So K cat equals Vmax divided by the enzyme concentration. We said for the Vmax we had a 1 millimolar per minute. So we have 1 times 10 to the minus 3 mole per liter and minute. Let's put the minute here. That was our Vmax. Bless you. And for our enzyme concentration, that's what we just calculated, 3.33 times 10 to the minus 8 mole per liter. Quite nicely, mole per liter cancel out. And if you put that into the calculator, you get a number of 30,000. We still have the minute here. So it would be 30,000 a minute to the power of minus 1, or per minute. What on earth does that tell you? It tells us that at its peak, every single enzyme molecule can deal with 30,000 substrate molecules per minute. That is 500 substrate molecules per second. Blimey, that's fast. So this is what K-cut tells us. K-cut tells us how fast a single molecule of the enzyme deals with substrate molecules. What's the capacity, if you like, of a single molecule of the enzyme? So we have 30,000 substrate molecules for a single one molecule of enzyme. Does that make sense? Yeah? And as I said, it's this three-step calculation. Calculate the grams of the enzyme, convert the grams into mole, and get the concentration of the enzyme. Easy peasy. Happy with that? Whoa. So, what I suggest now is can you quickly all stand up if you are able to stand? Okay, thank you very much. Sit down again. I just wanted the circulation to go a little bit, yeah, so that not all the blood is in the legs. And you consider doing a runner. Now another very important sort of comparison for enzymes, and that, ladies and gentlemen, I have to break to you, that is going to be your big challenge next year. When you do the second mini project, because you have to calculate next year and this year as well, you have to calculate what is called the specific activity. The specific activity of an enzyme. What is the specific activity? Well, with the K-cat, we basically calculate how many substrate molecules one enzyme molecule can deal with. And for that, we need the molecular mass of the enzyme, as you have just seen. But quite frequently, we don't know the molecular mass of the enzyme. So if we don't know the molecular mass of the enzyme, we can't calculate K-cat. But we can actually calculate the next best value for that, how good the enzyme is, by saying specific activity, and I call it spec-ac, is defined as the number of moles of substrate that can be converted per minute and per, say, milligram of enzyme. Let's see what the specific activity is in our case. So we said we take 10 microliter of enzyme of 1 milligram per milliliter stock, add it to a total volume of 3 milliliters, and eventually we get a Vmax of 1 millimolar per minute. Sometimes you will see that people don't use Vmax, Technically speaking, this is not okay. But sometimes it's really difficult to get a Vmax with just a few data points. So then in this case, very often people just go close to Vmax, make an estimate of Vmax. So I guess you probably get away if you go to, say, 90% of Vmax in your rate. You shouldn't do it below that. And I show you how you can calculate that in a minute. So ideally it would be Vmax, but if it is a little bit under Vmax, it's sort of okay. Not ideal, but it's okay. So, number of moles of the substrate. How do we do that? Number of milligrams of the enzyme. How do we do that? Well, actually, the enzyme we have dealt with already, because we said, how many grams of enzyme do we have? We said we have 1 milligram per milliliter, so that's 1 times 10 to the minus 3 gram per 1 times 10 to the minus 3 liter. And we use 10 microliters, so 10 times 10 to the minus 6 liters. Liter cancel out. And we have 10 times 10 to the minus 6 gram of the enzyme. Yeah, happy with that? That's basically exactly the same calculation that we've done for the K-cut. Now, let's see how many of the substrate per minute we turn over. So what we are looking for is mole per minute of substrate. Now we know that our Vmax is 1 millimolar per minute. So we have 1 times 10 to the minus 3 mole per minute and liter. That's 1 millimolar per minute. Yeah? And we have a volume of 3 milliliters. So times 3 times 10 to the minus 3 liter. Liter conveniently cancels out. And we have 3 times 10. If you multiply 10 to the minus 3 times 10 to the minus 3, you get 10 to the minus 6, just simply by adding the exponents. So you've got 3 times 10 to the minus 6. And what have we got? Mole per minute. Happy with that? So, for our specific activity, spec ac, we have our numbers of moles, and we just need to divide them by the amount of grams from the enzyme. So we have 3 times 10 to the minus 6 mole divided by 10 times 10 to the minus 6 gram, and we've got a minute here as well. Oh, look at that, cool. The 10 to the minus 6 just simply cancels out. And all we've got left is 3 over 10 the same as 0.3 mole per minute and gram. Or if you divide both by 1,000, the mole and the grams, that would be exactly the same as 0.3 millimole per milligram and minute. Alex is frowning. You just divide the mole by 1,000 and you divide the gram by 1,000. And it's still 0.3. Just actually what you could do is to prove that is right, you can cancel out one of the m's. But not the m from the minute, because then it would be just in. That makes sense? Yeah? What does that mean? It actually means that 1 milligram of the enzyme converts 0.3 millimole of the substrate in 1 minute. Not as, how should you say, nice an image as kcat, but if you don't have the molecular mass of the enzyme, then this is the next best thing that you can deal with. And it allows you actually to compare enzyme preparations. So for example, you have an enzyme preparation. Let's say you have preparation A, and you've got a preparation B. And preparation A has a specific activity of 100 millimole per minute and milligram of enzyme. And preparation B has 10 millimole per minute and milligram. Which preparation is more active? Of course, it's the preparation that gives you more substrate per milligram. So in this case, it would be A. A is more active. And in a way, you can, with this nice little thing, you can compare different preparations. Okay? Happy with that? Can you do that? There are actually exercises on the practice calculation website where you can practice these calculations. I told you that for the specific activity, you should really realistically be close or at Vmax. But we know that you will never reach Vmax. So, but you should be really at, say, a rate of at least 90% of Vmax. So your rate should be larger than 90% of Vmax. Now the big question is, what substrate concentration would you need for that? Actually, you have done that calculation, although you are not aware that you have done it. At least those of you who just recently submitted the coursework for Dr. Wei Feng. So, our rate, let's say our rate is 90% Vmax. So we have V equals 90% of Vmax. And I just simply write 90% as 90 over 100. Or that would be the same as 0.9 Vmax. That's 90%. Now, I want to find the substrate concentration that gives me 90% of Vmax. So let's just simply use our beloved Michaelis-Menten equation. Rate equals Vmax times the substrate concentration divided by Km plus the substrate concentration. And instead of V, I just simply write 0.9 times Vmax equals Vmax times S over Km plus S. Make sense? And what you see is the Vmax actually cancels out. So all I have left is 0.9 equals S over Km plus S. Now, of course, this is one equation, and there are two unknowns in it. I don't know S, I don't know Km. So the best outcome that we can get is S as a multiple of Km. But that's fine. That's not a big problem. Let's just quickly do that. So how do I solve this? How do I rearrange this equation and find S? Well, I multiply both sides with Km plus S. And on the left-hand side, I then have 0.9 times Km plus S equals, let's do it slowly, S times Km plus S divided by Km plus S. And on the right-hand side, you see that Km plus S cancels out. So all we have left is, let's multiply the 0.9 into the bracket. 0.9 times Km plus 0.9 times S. And on the right-hand side, all that's left is S. Make sense? And what I do now is just simply bring everything with S onto one side and everything that's not S on the other side. So we have 0.9 Km equals S minus 0.9 times S. Now for the right-hand side, what I can do is, instead of S, I can write 1S, right? So that's 1S here. 1 times S. And I can factor out S. So I have S 1 minus 0.9. What's 1 minus 0.9? Of course, that's 0.1. So we basically have 0.1 S equals 0.9 Km. Now it's really easy. I just simply divide both sides by 0.1, and I get S equals 0.9 divided by 0.1 times Km. I don't even need a calculator for that, because 0.9 divided by 0.1 gives me, thank you, 9 times Km. Or in other words, I get 90% of my rate when I have a substrate concentration that is 9 times the Km value. Of course, we could calculate 99%. Well, I leave that up to you. So there are plenty of practice questions, again, for that, on the practice calculation. If you want to ace your exam, I can already tell you that you might want to look at something like that. It will come up in the exam, I promise you. Right? No further questions? Fantastic. On Wednesday, I see you to discuss inhibitors. Don't be inhibited.